Welcome to this special class. Today, I'm not going to teach. I outsourced the task to Dr. Petar Veličković, who's going to talk about categorical deep learning. But before, I just want to briefly introduce him. He's a staff research scientist at Google DeepMind and also an affiliated lecturer at the University of Cambridge. He got his PhD in computer science from the University of Cambridge in the Trinity College, working with Pietro Liò. And his research in general concerns geometric deep learning, or in other words, creating neural network architectures that respect invariants and symmetries in data. And he has written a book on this, or how we call it, a proto book, whatever. To me, it reads very nicely, so I would call it a book. He's been very active on compositional learning and various other aspects we'll touch on today. So, in this class, we have seen applications in design, optimization, and this is another class of applications that I believe it's being quite successful of these compositional toolboxes. And that's why I'm very excited to have Petar. Let's make this interactive. So, we have 90 minutes. Petar will give a talk. If you have questions from the online audience, please post them and we will monitor them. If you have questions from the physical live audience, just raise your hand and we'll try to moderate the discussion. And without further ado, Petar, thank you again so much for coming, and the stage is yours.
Thank you so much for kindly inviting me to speak at your class, Jella, and thank you all for coming to listen to my talk today. The geometric deep learning book, which we will talk about a little bit shortly, is I would say still a proto book. In fact, MIT Press is currently pushing us to finish the book as soon as possible, but it's not so easy with the dynamicism of research today. As mentioned, I will be talking about categorical deep learning today. It is a topic that recently I co-developed with several co-authors from Google DeepMind and Symbolica AI. And we basically, we all had different motivations for why we came up with this work. But basically, the main reason why I wanted to jump into this is because I saw the limitations of the capabilities of geometric deep learning, and I basically got increasingly frustrated with using geometric deep learning to model things that I'm interested in. And that's why I felt a jump into the realm of category theory was required. As already mentioned by Joel, I would like this to be a relatively interactive experience, though keep in mind that I will not be able to look at Zoom in parallel with speaking. So my slides are going to be in a separate window. I will have specific parts where I'm going to explicitly pause and take any intermediate questions if you have them. And I would recommend that you ask the questions sooner rather than later, because the theoretical technical content is going to ramp up increasingly throughout the talk. And if some intermediate part doesn't make sense or you don't understand the motivation behind it, it's not going to be easier to justify later on. It's likely going to be harder to justify. So please feel free to make note of your questions. For those of you online, write them on the Zoom. For those of you who are in person, just wait for me to make my pause, and then please ask those questions promptly. Another thing that I will mention before we start is that my understanding is that everybody attending this already understands the basics of category theory. This talk was designed for an audience that doesn't necessarily know those basics. So there will be some slides that are geared towards maybe beginners in the space of categories and manipulating them. We will obviously go through those a little bit faster. I will still leave them sitting there because they might be a useful refresher. They might tell you a little bit about the kind of notation we use. And there might also be a few short exercises on the spot just to make sure everybody's still awake. So hopefully this is a good deal. And without further ado, we're going to dive into what will eventually lead us to our recent categorical deep learning paper, which is also titled An Algebraic Theory of Architectures. Before we dive into categories, though, as mentioned, I'm going to talk to you about why do we even need this, and I'm going to talk about it from the perspective of my own research. So there are basically things that I was very actively involved in over the past couple of years, primarily concerning geometric deep learning, as we previously mentioned. And so that we can understand better why did I feel the need to jump into the realm of categories, we are first going to talk about the realm of geometry, which is a strictly special case, as we will see later on. So in geometric deep learning, the main object, the principal concept that we are trying to study is that of a symmetry. Specifically, we want to study transformations of objects or data that leave that data for all intents and purposes unchanged, right? This is really important for designing deep learning architectures because we often have to fit systems with huge numbers of parameters with relatively smaller data sets, right? And the capacity of such a model vastly outstrips what the training data can support, leading to all sorts of issues like overfitting, cursive dimensionality, things like that. With geometric deep learning, we explicitly embed into our architectures certain symmetries, and we force the model to give us predictable answers when we apply symmetries on data. And this is the reason why it has proven to be a really powerful paradigm. Virtually any model which isn't just a straightforward multi-layer perceptron applied on your data is a model that has some geometric constraints. For example, even modern transformers that are applied in language models will feature some form of permutation symmetry and rotation symmetry embedded inside them. You're not concatenating all your tokens together and fitting that in an MLP. You actually have delimited token boundaries, and those tokens across boundaries are processed basically independently, followed by attention mechanisms, which are resistant to permutations of the computational structure. So already something that's already quite generic and applied across the board in modern AI systems has a lot of symmetries baked into it. So I think symmetries are worthwhile to study. And I believe that these concepts are best illustrated using specific examples. So here is one specific example that can illustrate symmetries. Imagine that you have data that lives on a triangle. So every single input is basically 3 different numbers, where each number corresponds to a different corner of the triangle, and you're storing features in those corners. What you can do to that triangle is you can do a 120-degree rotation to it. Those are the green arrows. Or you can do horizontal flips to that triangle. Those are the gray arrows. And for all intents and purposes, these transformations are still the same triangle. The main difference is that you're looking at it from a slightly different perspective. So if you want to, you could exploit that knowledge to design a triangle neural network that processes this data over triangles in a way that will process these rotated and flipped triangles in the same way as the original, right? This is one such concept. Now, in practice, in mathematics, we have a very nice way to formalize these collections of transformations using the concept of a group. The reason why groups emerge here is because if you think about this informal definition, a symmetry must leave an object unchanged. This immediately draws certain axioms to follow with it. The first one is that there must exist an identity transformation, and that has to be a symmetry. If I have 2 symmetries, F and G, I can always compose them. Their composition will also be a symmetry because neither of them loses any information about my data. And also, because symmetries do not change the underlying object, they also must be invertible. So there must exist an inverse to every single symmetry transformation. And moreover, that inverse must itself be a symmetry. So when you collect all of those different conditions together, you actually end up with exactly the axioms of a mathematical group. And for those of you who might need a refresher on that, I've listed all of the different axioms of groups on this slide. And just because I really like showing different symmetry groups, I also show you my favorite symmetry group, which are the symmetries of the Rubik's Cube. Okay, so this is basically the setting that we're working with in geometric deep learning. And once we have that concept, like once we understand that all the transformations we care about can be represented using a group, we can then use that to describe how to exploit different group symmetries inside neural networks. So how to design neural networks that are going to be provably resistant to these kinds of transformations. And the first such concept is we can build neural networks that are group invariant. What do we mean by this? We mean that a function is group invariant if no matter what group transformation I apply to my data, my model should still, or my function should still give me the same answer. So this is maybe the most basic form of symmetry inside the model. If I transform it predictably, this doesn't change the final answer I get. And hopefully by now you are familiar with convolutional neural networks, for example. Those are pretty standard neural network models applied over images, and they tend to embed the concept of shift invariance, which means that you can shift a particular object where it is in the image, but the final prediction that that object in the image should not change, right? So in this case, you have a picture of a bug, and you can also run your translation invariant model on a shifted picture of a bug. And if your model, if your convolutional model is resistant to these shift symmetries, then you're guaranteed that your output class will be the same for those two images, okay? This is something that is not an approximate property. This is a guaranteed full mathematical property that the architecture must satisfy. Now, obviously, invariance is a really cool property if you want exactly the same answer if you transform your inputs. But actually, very often, you don't necessarily want that. So, for example, if you're not, once again, in the domain of images, if you are not trying to just predict what's in the image, but rather extract certain properties of images, or even classify every individual pixel of the image, this here corresponds to an image segmentation task, right? So say you want to analyze a medical image and detect where are the organs, where are the blood vessels, where might be any cancerous tissue and stuff like that. If you shift that image, obviously the prediction of where the cancer is should not be exactly the same, right? Actually, the prediction of where the cancer is should shift together with the shift you applied to the image. And to do this, invariance is not enough. We actually need a more fine-grained concept. And this fine-grained concept we call equivariance. And I have this animation on the slide, which hopefully renders properly. Every time I cycle outside of my slide, it freezes, I think. But you can hopefully see the main concept of equivariance. Every single convolution that you apply in a convolutional neural network has this nice property. And specifically, when you have something that's shift equivariant, when I shift something inside my image, it will obviously change the result that I get, but the change is predictable. So as I shift my object, my prediction must shift together with the object. This is what equivariance is all for. And it's also something we can define. So I can have a neural network that takes a signal on my input and maps it onto some other signal on that same input, and this on that same domain. And we say that this function is group equivariant if no matter what group action I choose, it doesn't matter if I apply it on the input or output of the function. One interesting thing to note here is that invariance is actually a special case of equivariance for a specific way to express how group actions are represented. And this can be an interesting exercise for later to think exactly how this ends up being a special case. Okay, so using these core concepts, equivariance and invariance, we can build a huge zoo of possible neural network architectures by interchanging various building blocks. Those building blocks are equivariant layers that you apply on your input in a way that respects the symmetries of that input, but doesn't change the structure of that input, right? Because sometimes you might want to predict things on your input structure directly rather than one class for the whole input. We typically make these equivariant layers linear so that then we can compose them with any nonlinearity we want, like a ReLU or sigmoid or GelU or something like this. And well, if all we want are predictions on individual elements of our input domain, then we can just exchange equivariant layers and nonlinearities until we're ready to predict the answer. sometimes we might actually want to predict something over the entire domain, in which case we need this invariant layer at the end, which reduces our entire domain into just a single point, and it will predict things equivalently for symmetry transformed objects. We might also want to explore the hierarchical structure in our input by interchanging some pooling layers in the middle. Note that this is not a strict requirement. It's just there to encompass these ideas like 2x2 pooling in images and things like that. And it turns out that this blueprint is remarkably general. For the right choice of domain omega, where your data lives, and the symmetry group G of that domain, which governs which transformations of the input domain should be seen as symmetrical, just by choosing those, you can have several popular architectures pop out as special cases. One standard example that we discussed throughout the talk so far are convolutional neural networks that operate over grids or images, and they respect translation symmetry. And in fact, for those of you who know this, it's a standard result in signal processing that the only translation equivariant linear operator on grid data is the convolution. So in some sense, convolutional neural networks are not just one translation equivariant layer. They are the only possible linear translation equivariant layer. Any translation equivariant neural network over images must be a convolutional neural network. There does not exist anything else that satisfies this constraint. Okay? Then you can move on to some other choices of domain and symmetry groups. So you can recover things like graph neural networks by using your graph as the domain and the permutation symmetry group as your set of transformations. Actually, using the permutation group, you recover many other architectures like deep sets or even transformers. And you can get actually really cool results on some more exotic domains where your data might live by applying basically the same style of analysis. So for example, you can define, using our blueprint, spherical CNNs that operate over the surface of the sphere and are equivariant to the rotation group SO3 of 3D rotations. And why might we want to do neural networks over spheres? Well, anything that involves the surface of the Earth, like predicting the weather or processing astrophysical signals, you can imagine as being projected on the surface of the sphere. And you might want, it might not be a good idea to use a convolutional neural network on that surface of the sphere, because the closer you get to a pole, you're going to have bigger and bigger errors, right? So having a sphere will allow you to encode these kinds of symmetries more accurately. But you can go even beyond something homogeneous like a sphere, and we can go to arbitrary Riemannian manifolds and define various mesh CNN models that respect the local isometries of the manifold. Also, our blueprint allows you to elegantly combine two different symmetries in the same architecture. One very popular style of architectures that arisen after we released our initial protobook are these E3 GNNs. So these are graph neural networks that operate over geometric graphs like molecules, right? So a molecule is obviously a graph of atoms connected by chemical bonds. So you can have some sort of permutation symmetry on that graph. But also, these molecules are not just random abstract points. They are somewhere in three-dimensional space. And generally, if you assume your molecule is in a vacuum, you can rotate it or translate it or reflect it, and it's still the same molecule. So you can do additional transformations of the Euclidean group E3 on the coordinates of the individual atoms. And that acts on the molecule in conjunction with any permutation that you apply. Using our blueprint, we can define these E3 GNNs that respect both permutation symmetries and Euclidean group transformations. Perhaps the most popular approach that is explicitly equivariant to these kinds of transformations is AlphaFold 2, which recently was the centerpiece of a Nobel Prize in chemistry, right? So you can also discover some other objects like long short-term memories by studying time warping transformations on grids. There's a lot more detail on how to derive these things that you can find in our proto book and hopefully soon in the full book. So I won't dwell too much on how these things are derived. This was mainly there to give you hopefully some motivation for why GDL is already, as it is, quite powerful. Okay, so I'm now going to want to go beyond symmetries. And before I do that, I feel like it's important to kind of make sure that we're on the same page about geometric deep learning and why it's useful and how to build these architectures. So I'm going to pause here, maybe for a couple of, maybe a minute or two, and see if there are any questions about the material we have covered so far before we dive into categories.
Any questions? Any question from the online audience?
No. Yeah, I think there's some reason behind. So I talked about the similar topic in the first presentation. So
okay. So these are refreshers then.
Yes.
Nice.
I mean, this is good. This means I will have more time to talk about the more intense stuff. So, okay, good to know. Well, as we described in everything we covered so far, in geometric deep learning, we design neural networks that are fully resistant to symmetries. So we talked about invariance, where a symmetry applied on the input does not affect the output. And we also talked about equivariance, where the symmetry on the input does affect the output, but it affects it in the same predictable manner as it would affect the input. And this turned out to be sufficient to basically rediscover all of your fan favorite architectures in use today. So one might argue that, okay, maybe geometry and groups are sufficient to talk about architectures, and maybe this is a natural place to stop. But obviously, since I'm going to talk to you for another hour, I hope you can agree that probably there's more to this. And we will indeed talk a little bit about, are symmetries actually the whole story? And the way in which we're going to analyze this question is by looking at the symmetry group axioms one more time at a slightly more critical lens. So I'm repeating to you this slide from before, which shows all of the axioms of symmetry groups. And specifically, I want to call your attention to the inverse axiom and the closure axiom. So the inverse axiom assumes that every single transformation you care about has an inverse. So you're modeling resistance only to things that have no information loss. And also, we have this closure assumption that every pair of symmetries must compose to give you another symmetry. And this also is, I think, a pretty strict assumption that all pairs of things you care about must be composable with each other. In reality, this is definitely not covering every possible situation, because not all transformations you care about are invertible. So some transformations, you might really want your neural network to work well with those transformations, but they might delete half of your data. So how are you going to model that using a symmetry? You're not going to be able to model that using a symmetry. Also, in general terms, you cannot compose every pair of transformations. You can only compose a pair of transformations if the output type of the first one matches the input type of the second one, right? So this might be one motivation for going beyond what a symmetry can explain. And this was actually the main motivation for me personally. So some of you might be aware, my core area of research is neural algorithmic reasoning, where I try to explain and model the alignment of machine learning models and classical computation, like algorithms and data structures that you might typically encounter in an undergraduate computer science course. So I might be interested to kind of have these inductive biases baked into neural networks such that they will behave like an algorithm in one way or another. But not all algorithms maximally preserve information. In fact, for example, the filter algorithm on lists will delete any items in your list that don't conform to a particular parameter. So those you cannot invert. And as is the case in all programming language theory, you cannot compose all pairs of programs. You must have alignment between the output of the first program and the input of the second program. So it seems we actually do need a language that's more general than group theory, especially if we want to talk about these kinds of alignments. And specifically, we might want some perspective that will allow us to talk about structure, but in more generic computation, so not just symmetric computation. And this is where category theory steps in as a tool that can offer such a perspective. Now, I'm going to fast forward through what comes next, because as we discussed, I am assuming that everybody here has a primer of category theory already in place. So, but this is just to repeat it and maybe to introduce the specific notation I will be using in case that it differs from what you've seen before. So we're going to think of a category as a universe of objects and morphisms between them. These are the usual axioms that must be satisfied for every category. So unique identity morphism, all pairs of compatible morphisms must compose. and they must also commute with respective identities. And if we have any 3 composable morphisms, associativity holds. Typically, you can study these kinds of scenarios using commutative diagrams. So these kinds of diagrams where you have different objects as nodes in a graph and different morphisms as edges in a graph, and any pair of paths in such a diagram must yield identical results. Okay. I should just highlight this so that we're absolutely clear on it. A category generalizes a group because we still have identity transformations, but now we have one per each object. Not all morphisms need to be invertible. There's no condition on that. And also, not all pairs of morphisms can compose. Only the ones where the endpoint of the first one matches the start point of the second one. So there are very clear differences between a category and a group. Specifically, categories are more general. And one thing that's critical about this is that unlike what we might do in a group, we don't really assume any knowledge of what's inside these objects. And this allows us to focus on the structure of computation and not get bogged down in details. It's an excellent recipe for discovering connections between different fields, even if they're very disparate. And the standard example that is typically introduced when you study category theory is the set category, where your objects are sets and your morphisms are functions. So here is one example of 2 objects and a morphism in the set category. We have a set A and a set B, and the function mapping elements of A to elements of B. This is one particular pair of objects connected by a morphism. And what I mean by opaqueness is that actually when you draw a category, you have no visibility of what's inside these 2 sets. All you can see are there's an object A, there's an object B, and there is an arrow connecting A to B. You don't know anything about what's inside the sets. Now, maybe this is going to be obvious to everybody in the room, but one thing that was quite mind-blowing to me when I started studying category theory is that even though the category is oblivious to what's inside the sets, basically no data about the sets is dropped. You can use just the structure of the arrows to make sense of what's inside the sets. And to kind of derive this, which, as I said, initially to me was a mind-blowing result, we can start by discussing some special sets. Specifically, we can start with a 1-element set, which, depending on whether you come from functional programming or otherwise, you might see this denoted as open close parenthesis or unit. In both cases, it's a set with a single element. So what can you tell me about morphisms from any set to the unit set? How many morphisms are there?
Someone else.
Who wants to say something? We have this question already in the class.
I saw people already raising this.
Okay, so people have recognized that there is exactly one, right? So there exists exactly one function mapping any set to the unit set, the one that maps every single element to the unit element. And this structure actually uniquely defines the 1-element set up to isomorphism. So what this typically means is that we can find the 1-element set inside this category by hunting for this particular pattern where every other set has exactly one arrow pointing into it. You probably know this by now. This kind of structure is what's known as a terminal object, more generally. Inside the set category, the single element set is a terminal object. So every single set has exactly one function into it. Okay, so now that we know what is the single element set, we've identified it by looking at the arrows. Now we can look the other way around, right? So we have a single element set and any other set. And I've just, for convenience, numbered the elements of that set. So what can you tell me about morphisms from the unit set to any particular set? How many are there?
Can you hear him better?
I can't hear it very clearly. Can you repeat?
Yeah, it's the same number as the element in the set, so n, or
one.
cardinality.
Yeah. So it's the cardinality of the other set, and specifically these functions are exactly what's known as constant functions. In fact, in many functional programming languages, this is how constants are defined. Because in functional languages, everything needs to be a function. So one very easy way to functionally define a constant is just functions from unit to that particular type. And okay, great. So, but one thing that's great about having this collection of arrows is that there is, in some sense, a unique correspondence between every arrow and every element of that particular set. So, okay, we've identified our unit set. Now we have any particular set B that we care about. We can count the different morphisms coming into it, and we can actually, up to isomorphism, uniquely associate every arrow inside in this for these pair of objects as elements of B. So even though I only looked at morphisms, I never peeked inside the sets, I've been able to tell you everything about what's inside every single set in my category. And I think this is a pretty cool result. Specifically, we don't have a drastic loss of information, but we can still detect patterns in computation without focusing on the specifics of the data that's being computed over. And that's why I believe category theory is the perfect tool for these purposes. And generally, it's, as I said, a wonderful tool to connect disparate areas of math. Okay, so hopefully that makes sense. That should be relatively introductory material. We are now going to dive into how to categorify certain things that we are going to need in our categorical deep learning derivations. So as you probably know, neural networks operate over vectors, and they transform them into different vectors. So it might be really useful for us to reason about how vectors transform using this blueprint. And one standard choice to do that is to use the vect category. Vect category also has objects as sets, but those sets need to be equipped with certain structure of a vector space, to be precise. So what this means is that it's a set of vectors that needs to support vector addition, scalar multiplication, and all of the usual axioms you would expect of vector transformations, like associativity, distributivity, and so on. The morphisms are still functions between vector spaces, but specifically we focus on linear functions between different vector spaces. We already discussed before why focusing just on linear equivariants, for example, is a good idea, because those tend to be much easier to study, and you can get nonlinear behaviors by just composing linear equivariants with nonlinearities, like ReLUs or something like this. So generally, studying linear functions tends to be a good first approach. And actually, the study of vect is exactly the study of linear algebra. So there's a very nice correspondence between how the main matrix operations are done inside a neural network and what this collection of models is doing. Okay, so we've talked so far about what happens inside a single category and how those categories are organized. But actually, the power of category theory emerges when you start to allow multiple categories to interact. And the same way we can define functions between sets, you can, as you probably know, define functors between categories. Those affect both the objects and the morphisms. And I've just repeated here the axioms of a functor. So imagine you have two different categories, C and D. You can define a functor from one to the other. And that functor, capital F, maps both the objects and the morphisms of one category into the other. But it cannot be just any arbitrary mapping. It must be a mapping that preserves the structure inside the first. Or to be precise, not preserves. So a functor does not have to preserve structure, but it has to respect it. Okay? So what this means is that every identity arrow that you map from the input category must map to the corresponding identity arrow of where that object lands in the other category. And every functorial transformation of a composition must be the same as the composition of functorially transforming the individual morphisms. And these two conditions are sufficient to respect the structure of the category once you apply the functor. And especially, we will be very interested in functors that map one category to itself. Those functors are known as endofunctors. Okay, so I have a nice visual representation of functors. You've probably heard a lot about them so far, but maybe this picture helps you see them in an even more interesting light. So here is our usual commutative diagram of a category with three objects and different functions, identities, compositions highlighted. What a functor will do is it will map every single object and morphism in the first category into objects and morphisms of the second category, but it must be done in a way that preserves these nice structures, like these triangles that you saw in the first diagram. There should be triangles in the second diagram as well. Note, as I said, the structure only needs to be respected, not preserved. So this means that you could actually collapse this triangle into just a single point with identity morphisms between them. So map all these three objects to the same object and map all morphisms to just some combinations of identities, but or like self loops. But it must be done in a way that this commutative diagram still commutes in the other category. And one very nice way to kind of, in a layman's terms, understand what's happening is this really nice quote by John Bayes, which says that every sufficiently good analogy is yearning to become a functor. Okay. So moving on from functors to natural transformations. Much like functors allow you to connect two categories, you can also connect two functors together, and this gives you the natural transformation, which is one of the most powerful concepts in category theory. In fact, Eilenberg and MacLean originally invented functors for the purpose of defining naturality. You can study them by looking at two different functors, f and g, that map between the same two categories, c and d. And your natural transformation alpha maps the functor f to functor g. We use the double arrow here to denote that it's a natural transformation. And specifically how it works is you take every object in the first category, and for every object in the first category, the natural transformation will give you a morphism for that object, this alpha x. And this object maps the way in which this x object is mapped by both f and g and connects them together in the mapped category D. And it must be these alpha morphisms must be produced in a way that commutes with the two functors. So specifically, this composition must be satisfied. This composition equality must be satisfied for every single morphism that you have inside your original category. This is good to be visualized using diagrams. So once again, imagine you have this morphism x to y in your original category, and you have these two functors f and g, which will obviously map both x and y and f to different, possibly different objects and morphisms in the second category. So you have f of x goes to f of y using f of f. G of x goes to g of y using g of f. These structures must exist because of the structure of the functor. So what is a natural transformation? It really gives you this collection of these blue arrows, these alpha arrows, that connect the diagrams and create what is known as a naturality square. And this naturality square must commute. So you can either start with applying the first functor and then applying the morphism of f and then applying one alpha to get to whatever g would do. Or you can first apply the alpha and then the second mapped morphism. Those two will give you exactly the same outcome. And as you probably know, when you talk about natural transformations, usually you don't have to draw these two functors. You don't have to draw x, y, and f. Typically, one will only draw the naturality square, so the square of the four objects at the top. Okay, so I'm going to quickly recap on the specification, just so that everybody's on the same page about all of this content, because we talked about three different things: categories, functors, and natural transformations, and we talked about what is necessary to specify each one of them. So if you want to specify a category, you need to specify the objects and the morphisms, and if it's not trivial, you need to also describe how the morphisms compose and what are the identities. To specify a functor, you need to tell me what are the two categories that the functor relates. You need to specify how the objects are mapped by the between the two categories and how the morphisms are mapped between the two categories. And to specify a natural transformation, you need to tell me what are the two categories that the two functors are relating. You need to describe the two functors that the transformation is relating. And then you need to describe, for every object in the first category, you need to give me its corresponding alpha morphism, the component morphism in the second category that connects the naturality squares. Okay, this is another good place to make a pause. I've mostly talked about standard material, maybe using slightly different language than what you might have seen in previous lectures. So are there any questions on this material, or is everything clear?
Seems to be all clear here. What about the online audience?
I don't see any comments.
Okay.
So it should be good.
So good. We did a good job then.
I'm happy I helped perform a small sanity check. Okay. So now we're going to move on into the realm of monads. And specifically, we're going to talk about how we can relate those group actions that we cared about in geometric deep learning, right? If you remember, to build geometric deep learning models, we needed to reason about group actions. We can actually talk about group actions in category theory as well. We just need to use a special type of endofunctor known as a monad. A monad is a very universal mechanism to express contained computation in functional programming. I've given here a typical definition for a monad you might find, say, in Haskell. But it's a notoriously complicated concept to meaningfully explain. In fact, many functional programmers or category theorists will just tell you, all told, a monad in X is just a monad in a category of endofunctors. I don't see what the problem is. As you might expect, this explanation hasn't really resonated with beginner programmers in Haskell. And as a result, since the 1990s, the number of known monads tutorials has exploded. So what I'm going to do here is I'll add yet another tutorial to the list of tutorials. Hopefully it doesn't add to the confusion. Okay. So categorically, if you want to define a monad, you need to give me three things. It is a tuple M, eta, mu, where the first element, M, is an endofunctor. The second element, the eta, is a natural transformation called return. And this is a natural transformation between the identity functor on C and the endofunctor M. And we have another natural transformation, which we call join, which takes a composition of M with itself and gives you and relates it using a natural transformation to just M itself. So these things, the identity endofunctor and the functor composition, are defined as you would normally expect. And one nice way in which you can interpret what this M is doing is it is a container that specifies I want to do some kind of computation on this data. Okay, so the way to see that is to look at what these natural transformations actually give you, right? Remember what we talked about before. Natural transformations give you component morphisms. So eta will give you an arrow for every single x that maps something from the identity endofunctor, which is just x, to something that takes an m, so maps an x to an m of x. And what you can imagine this is it basically creates a new container around x saying, I want to do nothing with x. It's just identity, right? So when you resolve that m of x, you'll end up with just x. And the mu basically takes a nested computation. So it kind of has, I want to do this computation on x, then I want to do that computation of x. The mu allows you to reduce that into just a single wrapper, which says, I want to execute this and that on x. Okay?
So that interpreting X to be in the category, is X an object of the category here?
Yes, so X is an object of the category.
Okay.
Yeah. So, and these eta X and mu X are morphisms inside that category. So basically, obviously, it's not enough to just provide these arrows. You must have some basic structure satisfied inside these arrows. And specifically, you need these two diagrams to commute for this to be a legitimate monad. Hopefully, these diagrams are not too unintuitive. So the one on the left, you start with some computation around x, so m of x. You use eta to wrap another level of computation that is the identity around it. You then use mu to reduce that to just a single level. And because, as we said, the eta just creates a container without any additional computation required. So if you take that eta wrapped container and then you just reduce that back, you'll end up with the same computation you started from. So the m of x you start with and the m of x you end up with must be equal. Okay, so that's the left-hand side. On the right-hand side, we have associativity of mu. So if you have a triply nested computation, m of m of m of x, you can either choose to reduce the outer two m's or the inner two m's first, and then you use the mu to reduce the corresponding result. These should lead you to the same answer, right? Because it is the same computation. You're just choosing whether to first resolve the inner levels or the outer levels first. But they will all lead to the same answer at the end.
So, Petar, there is a question from Juan Servino, whether M has to be invertible.
So this is the part where my knowledge of category might prove a little bit of a blocker, because M here is a functor, so an endofunctor, and I am not completely sure how to define invertibility of functors. So this is something that might warrant more discussion later. But basically, because we're not talking about invertibility of any particular M here, right? We're talking about wrapping M in basically an identity or no-op transformation, and then reducing that to be left with back where we came from. But yeah, M is really just another term where where these kinds of M's arise is the so-called Cleasley category. So that's another kind of structure that you might want to study in this particular domain. Okay, so one standard example of monads is the power set monad P on the set category. So specifically, what happens when you wrap a particular set X into the power set monad? It basically says, I want to express this set using its power set, so all of its subsets. Okay? And as you know, because P is an endofunctor, it must map not just elements, but also morphisms. So every function from set X to set Y must become now a function between the power sets, but it's very easy to distribute X across. All you have to do is look at every single subset in P of X and map it to the corresponding P of Y. Additionally, we need to define eta and mu in this case. So eta just takes a set X and wraps it around its own power set. And mu of X takes a power set of a power set and reduces it to just a single power set by basically computing a big union over all of the elements inside the power set of power sets. And what we've all come here for is to discuss group actions as monads. Because as I said to you when we started talking about monads, we can describe actions of groups using monads. Specifically, you can describe group actions using this particular monad, G times blank, eta mu, where first let's talk about G times blank. So this is an endofunctor mapping set to set, and it maps every single set X to a product G times X, and every function F to something that maps G times X to G times Y, and just basically it instantiates this pair of group action and X and maps it to group action of F of X, right? So you can imagine this G times blank is basically a wrapper around the computation of I want to apply this group transformation to my data, right? I haven't yet done it. We will talk exactly how to do that a little bit later, but this is the main idea. So G times blank is something that takes a set that holds my data, and it says I want to apply something from G into like on this data. Now eta, as you might expect then, just takes a particular set X and maps all of its elements to just EX. So it's the identity group element. Like I want to apply the identity transformation to this data. Obviously, this will do nothing, but it will represent it in the same container form that you can otherwise use. And as you also might expect, mu, which composes a G of blank to just G of blank, takes this sort of nested group computation intent and just represents it as a single intent which composes the two group actions, right? So saying I want to apply H to my data, then I want to apply G to the result of that, is the same as saying I want to apply G compose H to my original data, right? So this is how you can specify group actions using a monad. Now, as I just mentioned, monads will tell you how to compose group actions, but they don't yet allow you to actually execute it. And to do this, we need just a little bit more machinery. And that machinery we need is called an algebra. So generally speaking, objects in category theory that allow you to execute computations stored inside other objects, they are generally known as algebras. And what's very important about this is that computations might execute differently depending on what's the object you're acting on, right? So this, G of X, right? It might execute differently depending on what is the set where X is coming from. And one very simple example of that is, let's imagine our group action is a permutation. And we might want to apply it both to node features, which is typically a matrix of size number of objects times number of features. This is the X over here. Or adjacency matrices of a graph, which is number of nodes times number of nodes, right? The permutation group action will act differently on these two objects. If your data comes from node features, then you just apply the permutation matrix to the to the rows of this matrix by doing px. But if you're transforming adjacency matrices, you need to permute both the rows and the columns of the adjacency matrix. And this gives you the PAP transposed expression. So this is the key idea. You're acting with the same permutation object, but the way in which you act will be different depending on the set your data is coming from. And this is why we don't define an algebra with respect to an entire monad. We need to define it relative to an object. So with that in mind, we can define an algebra for our monad. And this algebra is a pair of an object A, which we call a carrier object. So that's the thing that we wrapped our computation around and that we want to execute. And we also have a structure map, which takes a container and reduces it to what was inside the container after we do the transformation. And that's a morphism in our category. Of course, as before, you cannot do this in any arbitrary way. You must do this in a way that causes certain diagrams to commute. And it's these two particular diagrams that you see on the slide. So if I have any particular set A, I can use my return natural transformation to wrap it in some identity computation, then use my structure map to reduce it back. These two must be the same, right? Because the eta does not create any new computation. It just wraps it in the identity. And similarly, if you have a nested structure of two monadic computations, you can either decide to reduce them using the join operation, the join natural transformation, and then just run your algebra to reduce. Or you can apply your algebra 2 times in a row. Those two need to give you the same answer. So the algebra needs to respect the structure inside the monad. As long as these two are satisfied, this is a valid algebra. And now that you have this concept, you have a group action monad and you have an algebra for that monad, you can finally execute group actions and transform data. So specifically, group actions of a symmetry group G are exactly algebras for the group action monad G times blank. Here is a very simple example. Let's imagine we want to act on an image, so some width times height grid of pixels. And we act on it using the translation group. So our G is just an amount of translation on the width space times the translation on the height space. And we assume that our carrier object, so the object that the algebra is acting on, is just R to the W times H. So this is literally just matrices where in every pixel we put a single number. The structure map that you get is then just the translation map, which, as we described before, takes G times blank. So G is ZW times ZH times our carrier object. And that just reduces it to a transformed carrier object. And you would define this in the usual way. So you apply a shift by I prime J prime on your pixel feature matrix X. And if you want to look it up in a particular position ij, all you have to do is appropriately shift I and shift j to get these numbers. Of course, this is hiding a subtle detail that for these to be symmetries, they need to be cyclical permutations. So data that gets over the boundary of the grid must reappear on the other side. So treat these I minus I primes, j minus j primes as done in a modular way. So you always take the modulus with the height and the width. If you do that, this is still a symmetry transformation. Okay, so once you have this, now we can finally talk about how to define equivariant layers. And this was the crux of geometric deep learning, right? Now, monad algebras will allow us to talk about sets of possible inputs of our networks and sets of possible outputs for our networks, and also talk about how those inputs and outputs transform using symmetry groups. But we haven't yet specified a neural network layer, so some function that will take us from the input to the output, right? And to do that, we need to talk about transformations between two different carrier objects, and they might have their different algebras attached to them. And this, if it respects the structure of the monad algebra, is a monad algebra homomorphism. And this is what we will describe next. I see there's a hand raised.
Yes. I was wondering whether this is, you might know whether this is the case. Is this analogous to how in physics you might have a system and there are all these relationships, and then you apply, say, a change of observer would then be a symmetric transformation of your entire system, right? If I spin on my chair, the laws of physics are the same. So all these transformations you're doing to every stage. So if I spin on my chair, I'd have to modify the location of everything, the velocity of everything, etc. If I make all these modifications, my system fundamentally stays the same. Is that the sort of thing we're talking about?
Yes, exactly. And maybe to give you a more concrete kind of historical physics pointer to this, a lot of the foundations behind geometric deep learning were laid by Felix Klein in his so-called Erlangen program, where he used it to unify different geometries in mathematics. And one of his colleagues, Emmy Noether, used those exact same principles to derive what is known as Noether's theorem in physics, which basically says that all laws of conservation in physics are a result of a certain equivariance transformation. So assuming, for example, that your experiment will give the same results today and tomorrow, these kinds of things.
Yeah. No, that's awesome. I think for me, at least, thinking of it in terms of these are different systems and there's something like a change of observer is just intuitive. Yeah. More intuitive. Thank you.
Right. Thanks for asking. That's a great question. Okay. So now we have our objects A and B, and we have the algebras attached to them, right? So now we want to describe our function, our neural network. So something that will map our A to our B, but in a way that will respect the structure in the monad, right? Remember, we use the monad M to describe the collection of group actions. And now we want to kind of specify what are the allowed functions from A to B that will respect the way the monad transforms A and B, right? And strictly speaking, we take, so two objects A and B, we take two monad algebras defined over them, and a monad algebra homomorphism is really no more or less than a morphism from A to B that makes the following diagram commute. That's really the main thing it does. So what this diagram is saying is that if I have a monad transformed A, I can either first reduce it by applying my A algebra and then apply my neural network, or I can apply my neural network inside the container to get a B and then reduce it using the B algebra, and this must give me the same result. This is the crux of how to define a monad algebra homomorphism. And okay, so look at this diagram. I'm now going to instantiate it using the image translation example I showed you before. So all I've done here, this is exactly the same diagram as before, but now my monad M is a group action monad for example, translation. So G is now my set of Z height times Z width. and my carrier objects are just k or k prime dimensional features on my image. So something of the shape width times height times number of features in every pixel. So, and obviously my algebras are now just translations, and my function f is a neural network mapping images to images, right? So what does this diagram looks like here? It means I can either first translate my image, then apply f, or first apply f, then translate my image. Now, this should sound very familiar, right? Because I've talked about this exact diagram at the start of the lecture, right? This constraint here is actually exactly shift equivariance. And of course, we've used here the very specific example of shifts, but it generalizes to any pair of algebras for any possible symmetry group monad you want to use. And I hope you can see how this generic equation is basically all of geometric deep learning. Like, I choose my symmetry group, I choose my carrier objects for A and B and their algebras, and that's it. Like, this gives me an equivariance constraint. So maybe the main takeaway of, well, one of the main takeaways I'd like you to take from the talk today is that equivariant maps, the cornerstone of geometric deep learning, because in geometric deep learning, we basically express everything just using equivariant maps. They're no more or less than group action monad algebra homomorphisms, which when I say it to a lay audience, it causes their heads to spin for a little bit. I hope in this audience, this makes total sense now that we've derived every single part of it. But yeah, this is really one of the key results. Like, everything we're doing with categories can express the entirety of geometric deep learning, which maybe doesn't sound so surprising, but it's still really useful to see you need relatively simple objects to describe all of this. And I'll leave it as an exercise for you to describe how to specify invariant maps, which, as we've shown before, are a special case of equivariant maps. This is once again a good place to take a small break and just ask, are there any questions about this, or is the entire derivation clear?
Questions? One question. One question I had was, maybe you're getting to it, but like, this is great. Like, it's super interesting to describe the sort of group symmetries in this kind of categorical way. What are there new things that come out of that? Like, are there discoveries that kind of follow from this, I guess, or if you're getting to that, we can leave it. Yeah. Yeah,
we're definitely going to get there. So we're going to talk about equivariance to certain computer science concepts next. So stick around. Hopefully it will get more interesting. But yeah, so far it was just recategorization of everything that was in GDL, which I felt was a important first step before we can justify going beyond that.
Makes sense.
Any other questions?
I have a question. Yeah, I have a question too, if I...
Mm-hmm.
So I love equivariance, but sometimes it might feel a little bit too restrictive. I mean, you showed this slide at the beginning, kind of everything needs to be equivariant to preserve equivariance. And in a lot of ways, a lot of problems that we have in practice are not necessarily equivariant. At least that's what a reviewer too told me. So my question is, what is the general, in this like abstraction of equivariance, and where can I break something that I can come back to a quasi-equivariance thing? I guess a lot of these things are new to me, so, but yeah, that would be for example, when you apply a non-equivariant, I don't know, non-linearity, for example, things break. What would that look in this world, in a way? Thank you.
Right. So basically, we don't talk so much about the effects of what will happen when you have a non-equivariant architecture applied to equivariant data. Though, if you look at, I think, chapter 2 of the book, we talk a little bit about some specific bounds on the generalization error that you will get. So it's a function of your data set and the desired amount of error you want, right? So strictly speaking, the message is obviously equivariance will help you get better generalization error on equivariant data with smaller data sets. That's generally the message. One message that people are currently trying to pitch is that if you have a lot of data, the equivariance isn't that important. I actually think that that's too general. So as I said at the beginning, even modern generic architectures like transformers still have permutation symmetry and they still have rotation symmetry. They're not just arbitrary functions. So they have very specific token boundaries. However, they do often, like with AlphaFold 3, for example, it completely drops the rotational equivariance assumption and it just replaces it with data augmentation. And it seems to work quite well at scale. There was a really nice recent paper that I highly recommend you to check out. It's from Taco Cohen and a few other authors on does equivariance matter at scale? So in this paper, they literally tried to explore what would happen if we took an equivariant architecture and tried to derive scaling laws for it like we would do for a non-equivariant architecture. And actually what they find is that, okay, we know already that equivariance helps at small data scales, but actually it helps also at large data scales. You just need to do a more thorough hyperparameter search that's tuned for the equivariant architecture. The problem with current approaches is that someone just takes a state-of-the-art non-equivariant model, replaces it with an equivariance condition without changing any other hyperparameter. And this basically leads many people to find that, oh, the non-equivariant architecture is equally good because it has a lot of data that kind of teaches it the equivariance. What happens in reality in most cases is that the sweep of hyperparameters was not thorough enough for the equivariant model, because equivariant model actually has different learning dynamics to the non-equivariant model, and those need to be taken into account. Of course, there is another trade-off, which is that the computation time of the equivariant model might be higher, especially if you have more complex symmetry groups. This obviously is a trade-off that depends on the specific problem you care about, the amount of data you have, things like that. But yeah, like what I should say is that this specific blueprint, everything we discuss here, doesn't deal that much with the question of should you or should you not, just keeping you honest about which assumption your architecture is making, right? So you assume a domain, you assume a symmetry group. This is the layer that is equivariant for that symmetry group. No more, no less. I hope that answers your question. Okay.
I have one last.
There was another question.
I have one last question, which is, but maybe much simpler than the previous two questions, which was, I just wanted to clarify the blueprint here. So in practice, what this blueprint, what would be the blueprint here? It would be, let's define our symmetry. We then define, based on that symmetry, we then define our algebras, and then based on that algebra, we can design our network there.
Mm-hmm. Yeah, I mean, it's usually going to be, as we saw at the beginning, like some composition of linear equivariant functions and pointwise nonlinearities. And then after that, well, if you need invariance, you can strap on invariance at the end. But that's typically the blueprint applied. Equivariant to nonlinearity, and so on, where the exact equation for the equivariant model you get through this analysis.
Oh, they say equivariant, nonlinear, you mean like layers of the neural net?
Yeah, exactly.
Yeah, cool.
Okay, so it's useful to just briefly note, because I actually just mentioned this, right? Everything we've done so far gives you not layers, but constraints. So in order to actually solve these constraints and get expressions for our neural network function f, you typically need to materialize this diagram in some category, such as vect, where your objects now become matrices or vector spaces. And or for neural networks, you might prefer the category of affine spaces, and then solve the constraints explicitly inside this category to basically get weight sharing constraints on your architecture. So which neural network parameters in your matrices have to be shared, which of them have to be zero, things like that. So for example, if we assume that our function mapping images to images is expressible as some matrix multiplication that maps our features of k dimensions to features of k prime dimensions, you can actually use our constraint to derive weight sharing instructions for this matrix, and it actually leads to the usual circulant matrix definition for translation invariance. As an exercise, you can try to derive this for simple 2-pixel images. So width is 2 and height is 1. Now, I want to talk about a little bit in the time we have left about going beyond geometric deep learning and into the realm of purely categorical deep learning. The main thing is that when we defined the monad algebra homomorphisms, we never actually needed the monad axioms in this, right? So we can actually generalize this concept not just to monads, but to arbitrary endofunctors. And this is our first step beyond pure group equivariance. So an endofunctor algebra is, as before, it's a pair of an object and a structure map. And now I'm calling my endofunctor F rather than M to denote that it doesn't have the monadic axioms attached to it. And there's no specific, natural transformations that you have. Examples of these endofunctor algebras are actually abundant in computer science. So they're an excellent way to talk about quote unquote equivariance to computer science constructs. One standard example of this are lists. So lists, as you probably know, are a standard data type in most programming languages. And they can be defined using endofunctor algebras for this guy over here, 1 plus a times blank. So this is an endofunctor from set to set. And list of A is a set of all lists of elements coming from A. And we have nil and cons as two special ways in which lists can be constructed. And so those pairs of maps, nil looks at the single element set part of this plus and maps it to the 0 element list. And the A times blank part is mapped to a list where A is the head of the list and the remainder is the tail of the list. And this is a nice inductive way to describe lists as either an empty list or a concatenation of an element with the remainder. It's very typical in functional programming languages. And you can now describe, just like we described monad algebra homomorphisms, we can describe endofunctor algebra homomorphisms. The main difference, the diagram is exactly the same as before. The main difference is that now I'm using F rather than an M. And if you do something in the case of lists, so once again, our transformed object, so we want to find some functions mapping list of A to some particular output. And on the left-hand side, we have our 1 plus A times list of A object and nil cons as the algebra that reduces it to just a single list. So the algebra here tells you how to construct lists iteratively. You can either apply your function. So this gives you a new type of condition. You can either apply your neural network on lists to get just one output of type X, or you can apply this function F to the tail of the list you've constructed and then apply some specific algebra functions to reduce that to X. And these two should give you the same outcome, right? Now, these R0, R1 are some specific specifiers of computations on lists that you might want your network to learn to imitate, right? And specifically, it gives you these kinds of constraints, which we cannot really call equivariance constraints anymore because the operation of consing things onto a list is not a symmetry, right? So specifically, if you look at the diagram, it says that applying our neural network to the empty list needs to give us R0 of the unit. And similarly, applying it to a cons is the same as applying this function R1 to the head of the list and applying the network to the remainder. This type of constraint you could not express using geometric deep learning, but it's a very intuitive constraint for a neural network to have, right? It's saying that your neural network f of r must align with a fold operation that uses R0 to process the empty list and R1 to iteratively process a list, right? And this is, as I said, very similar to group equivariance, but the operations on the left-hand side are not symmetries. Cons does not leave a list unchanged. So this is a very intuitive constraint, but one which you could not have expressed ever using geometric deep learning. And one other thing to note is that you're basically aligning your neural network to the computation specified by R0 and R1, which is the specific function used in the fold operation of the list. Now, two things that I want to mention, and then we'll have hopefully some time for questions, is that the picture I showed you so far with mapping these diagrams into vect only allows you to deal with linear equivariance constraints, and it doesn't explicitly talk about the parameters. But it turns out that you can take these concepts and actually express them in a way that will allow you to talk about entire architectures and parameters. You just need to step from one categories into two categories. Now, once again, I hope that these concepts have been covered in previous lectures. In two categories, you have objects, you have morphisms, and you also have morphisms between morphisms, which are called two morphisms. And actually, in a way, we've already been secretly working in a two category all this time, because you can think about the category of categories called CAT, where your objects are categories, your morphisms are functors, and your two morphisms are natural transformations. So specifically, the two categories that we can use to talk about the parameters of a neural network as well as its computations is the parametric category, para, which is actually very similar to sets. So the objects in para are still sets, but the main difference is that the morphisms are now parametric. So there is some f which maps A to B, but that f also depends on a set of parameters p. So your morphisms now take a p and an f to be specified. And basically, this is the same as if you have objects A and B in set and a morphism that takes P times A and maps it to B, right? And you can often represent this graphically in a very neat way. So you have this box for the function f, and it takes A and also parameters and outputs B. Now, one thing that you are allowed to do here is it allows you to talk about maybe more interesting kinds of composition. So morphisms in para will compose by just chaining their computations. So imagine I have a parametric function from A to B and a parametric function from B to C. This is the same as specifying a single box mapping from A to C, and my parameters now come from the tensor product of the parameters of the first one and the parameters of the second one, right? So there's a very natural way in which we can compose two morphisms here. But we also allow ourselves to reparametrize, and that's where the two morphisms come into play. Specifically, we can go from a function pf, so with parameters p and function f, we can map that to a function fr with parameters p prime. And what this transformation is allowing us to do is it's allowing us to reparametrize what's coming into a function. So if we want to express our function with some different set of parameters p prime, as long as we have an appropriate reparametrization map, which maps p prime to p, this allows us to express the original fp as something frp prime, right? This is still the same thing. And one thing why this might be useful, for example, is if we want to talk about weight tying. So remember, in weight sharing, we talked about having identical weights in the same layer. With weight tying, we can talk about weights being identical across different layers of the neural network, right? This is something we weren't able to do with the previous diagrams. So specifically, if I have this composed function, x to y, which takes two sets of parameters, I can use my reparametrization trick by taking only one set of parameters and composing it with the copy map. And this now forces the two different layers to have exactly the same parameters, right? This copy operation forces that. And this is something that can help us express things like recurrent neural networks, which we could not obviously talk about in the previous diagrams, because the previous diagrams will talk about a single linear layer. They won't tell us about equality across different linear layers. Now, you have a two category like para. You can express entire neural networks, track all of their parameters, and now you can talk about constraints that span multiple layers, not just a single layer of the architecture. And you might be now tempted to just rebuild all of those endofunctor algebra stuff that we talked about before and build homomorphisms between those algebras. And you can definitely do that, but in a two category, the picture is not as clear as it used to be. In a basic category, you only have a situation on the left here, but with two morphisms, you now have three different kinds of commutative diagrams that you can build, depending on whether there is a two arrow that maps one path to another path, right? So there's four possible situations, and those situations, depending on what kind of two morphism connects the two paths, are either, so you have commutative diagram, so where they're equal, pseudo-commutative, where there's an natural isomorphism mapping from one to the other, and you have lax and collax commutativity, where there is a two morphism that maps one path to the other or the other way around. And we believe that this is a pretty exciting area to explore further. We cannot claim to have explored it to its natural limits in the paper as it is, but we did focus a little bit on analyzing just this guy over here, so the lax commutative algebras and their homomorphisms. And already that, in and of itself, was sufficient to uncover the standard types of weight tying that you see in recursive neural networks and recurrent neural networks. So it's already quite powerful. And once again, this kind of analysis where we explicitly talk about parameters and where different parameters need to be shared is not something you could have done with geometric deep learning alone. So with that in mind, as a simple demonstration of what the blueprint can do, I stress to you that this deep learning picture is very rich, and it's something that we formed quite recently. Our categorical deep learning paper was published at ICML only 4 or 5 months ago. And as such, we invite you to check it out and to contribute. You can find all the details and the paper, as well as our basics course on Cats for AI at categoricaldeeplearning.com. I should mention, while Cats for AI gives you a rudimentary introduction to the topic, which maybe you already know, it also has some really nice seminars from prestigious mathematicians and deep learners like Taco Cohen, Tyden A. Bradley, and one I'm personally proudest of, David Spivak. So we have talks from all of them that have volunteered special seminars to talk about the connections of category theory and deep learning. So I invite you to check out the Cats for AI contents as well as reading the paper. And if you want to make some contributions, please take a crack at it. Please reach out to us. We're very keen to hear about what you can come up with. And lastly, if you ever get stuck on a term and like to understand it better, you probably know this really well. NLab Wikipedia for categories is arguably the best resource. One thing to bear in mind, if you're not a mathematician, it's mostly written by mathematicians for mathematicians, and most articles are written under the assumption you already understand many other things. So beware of rabbit holes that I fall into every single day ever since I started studying this topic. That was my last slide. Thank you very much. Hope you enjoyed it.
Very nice. Any question for Petar? Yes.
Okay.
Go ahead.
Yeah. Hi, Petar. It's really cool to see you again, actually. I mean, 3 years ago, you gave a talk at the University of Amsterdam about graph learning, and now it's really fun to see how you also progress into more abstract spaces. One question I had was, the category theory approach, right, is generalizing on a lot of work that has already been done in the set theory. So I was wondering how what you're currently working on relates to things that we have seen in differential privacy and in general domain and codomain set mapping that has been a focus of work, especially 4 or 5 years ago.
Right. Thank you for the remark. Actually, the camera is not facing you, so I cannot see you, but it's good to see you again. Basically, thanks for the question concerning the relationships to set theory. I would say that there are many deep connections that we can exploit here, not just if we focus only on sets, but also even if we focus only on monoids. So monoids are already one step of generality ahead of groups, and they're actually categories with only a single object. So this is really great when you can assume that all your computations compose. So they're great to talk about repetitive computations, but they are not enough to talk about arbitrary sets and how they interact with each other. There's many specific special cases where we expect this to be particularly applicable. In fact, in all of the examples I showed you today, we've used the set category or small specializations of the set category pretty much throughout, right? So I suspect many results that relate to sets specifically are going to be rather applicable in deep learning. I wouldn't be able to comment on the specific connections, just to say that there's going to be many of them. Yeah.
Thank you.
Yes.
Yeah. So so you nicely showed how we can formalize some sort of invariance with respect to things we might care about, folding, that sort of thing. So my question is basically how one translates these constraints one gets, which one can instantiate in vector or whatever, or f, how one then gets the right sort of formulas for the parameters. Because even in the case of having some sort of basic symmetry invariance, this seems kind of a difficult thing to derive, for learning exactly how the parameters have to be, shared and so on. And then I imagine that for things like fold equivariance or whatever, things wouldn't get much easier. So is there a principled way you can convert these constraints into new reparameterizations on your space that you can actually learn on? Or is that something you have to kind of come up with in each example you're interested in?
Right. So that's a great question. And this is, to be honest, partially a limitation of geometric deep learning as well. So one of the reasons why we focus on linear equivariance is because they tend to be easier to solve than nonlinear equivariance. So in some cases, like translation equivariance, we know it's a known fact in signal processing that it has to be a convolution. in the case of, say, permutation symmetry, it's still kind of a ongoing discussion on like whether single-step graph neural networks that like do only local aggregation are sufficient to model anything you might care about, or maybe we need to do more than that. So it's still an open problem depending on the complexity of the group. Some groups are simpler. So for example, if you deal with things like rotations and translations, you can talk about these spherical harmonics, which are the irreducible representations of that group, and then everything maps to and from those representations. And these things are the foundation of things like SC3 transformers and stuff like that. So in some cases, you can apply really clever math to characterize every single transformation you care about and then express it as kind of mappings to and from this space. In other cases, as you said, it gives you a constraint, which you can resolve either by searching for some special case solutions and proving that they work, or by doing maybe not solving them, but doing data augmentation in a principled manner. So yeah, there's no unified blueprint, at least none that I'm aware of, to help you solve these constraints in general. But there are many special cases where we sort of know what we need to do.
Okay, thank you. Any other questions, Petar? Or there is one from Vincent online.
Oh,
yeah.
I was curious because when it comes to attention, we are trying to find the relationship between every token and each other token. So we're trying to find length squared relationships, which then leads to a length squared compute and transfer cost. So that sort of n squared number of relationships we're trying to find, it then necessarily leads to the computation cost. So I was wondering whether the type of symmetry we're looking for, so for example, permutation symmetry, has a necessary relationship to the algorithmic complexity of an algorithm.
So this is a great point. I would say it has a necessary relationship to maybe the upper bound of the complexity of the algorithm. The reality is that sometimes you don't need the full expressivity of the object that you're using. So for example, since you mentioned adjacency matrices and how they compute relations in attention, yes, in the worst case scenario, you need to compute a quadratic amount of items, which then means you have to do that many steps. There exist tricks like flash attention that allow you to do things more efficiently in the space domain, but the time complexity is still quadratic. However, you could decide to look at a more sparse graph representation, right? So you might decide that certain pairs of objects will not communicate and represent them using an edge list rather than an adjacency matrix. So now your permutation acts by relabeling your objects. And this now becomes the more general V plus E complexity rather than the V squared, right? So I would say it's a function of both the group you choose and the carrier object you choose to put that data on, if that makes sense.
Yeah, interesting. Thank you. Because I was also thinking about windowed attention removes the quadratic factor, but it also changes the type of symmetry we were looking for. It no longer becomes permutation symmetric. It becomes like convolution, effectively. That's what a windowing is. So
I would say it actually adds the windowing symmetry on top of the permutation one. So there's still a permutation, but now you have to permute the local edges together with your nodes. That's really the difference.
Yeah, interesting.
Yeah.
Thank you, Vincent. Any other question?
yes, following up question about the question of how do we actually get a form of neural network or general structure that satisfies this constraint. I was supposing that the last part of your lecture, of the talk, that some repermutation would do the trick. I was about to ask the question, but I'm not sure if you have an answer to it. So maybe we can do, is it possible that in some cases we can do some clever repermutation that can take any parameter and do some trick, and then the resulting form will be satisfying the constraint? So that's a question that I was about to ask.
So I believe, but I'm not completely certain of this part with the 2-lax algebra derivation was done by mostly my co-authors, but I believe they heavily rely on the reparameterizations in para to basically connect these things to the free monad and derive, I think, exact weight time constraints as a result of the specifics of the two morphisms, the two algebras that they want to be resistant to. So in this case, at least, but there's like 20 pages of it in the appendix of the paper, there might be some explicit reparameterizations that will give you these exact data flow constraints arising as a result of analyzing the algebras. But I wouldn't be able to tell you that for sure because I did not work on that part of the paper. That's at least how they've marketed it to me.
Okay, thank you.
All right, we are at time. Thank you very much, Petar, again for the talk. It was cool. It showed another kind of application, and it's also exciting because there's so many new things to do. So we have to be in touch and update each other because this is a nice venture. And yeah, I tell students to reach out in case they have other questions going forward.
Also, I should stress that I am very available both like via email and via social media. So if you have any questions afterwards, please feel free to reach out. I'm very happy to talk about these things. And thanks for having me, of course.
Thank you again. Thank you so much. And enjoy your evening, guys. Bye-bye.
Bye, everyone.